We now look at an endothermic change from a theoretical perspective to show how energy flows from the surroundings into a system. In endothermic chemical changes, the potential energy of the products is more than that of the reactants. Since energy cannot be created nor be destroyed, the particles of a system lose kinetic energy, which is changed into potential energy. This sudden decrease in kinetic energy of the particles of a system results in a lowering of the temperature, since temperature depends on the average kinetic energy of the particles. At this point, the amount of energy of the system remains the same, since only a transformation of energy has taken place. However, the container, the beaker, etc., in which the reaction takes place, and the environment are left at a higher temperature than the reactant system. Initially, the container feels cold because energy is absorbed from it by the system, which is now at a lower temperature. However, with time, the system and container will gain energy from the air, etc., until they attain their initial temperatures. The net result is that the chemical system gains energy from the surroundings. So this figure here shows the interchange of potential energy and kinetic energy between the reactants and products of an endothermic change, and it is exemplified by dissolving ammonium nitrate in water. So the ammonium nitrate and water have low potential energy but high kinetic energy. But as the ammonium nitrate dissolves in water, they gain higher potential energy, but there is a lowering of the kinetic energy of the system. And this can be exemplified again by these figures here. Ammonium nitrate is getting dissolved in water to form ammonium nitrate solution. This is the temperature of the water alone. When ammonium nitrate is added to water, there is a marked decrease in temperature. However, because the system now is at a lower temperature than the temperature of the environment, heat from the environment flows into the system until it attains its original temperature. We're talking about the reaction taking place in a closed system, not an isolated system. What would have happened if an isolated system was used? This is the temperature of the water and ammonium chloride just before reaction, and you can see that the temperature is the same as the ambient temperature of 23 degrees Celsius. In this isolated system now, there should have been ammonium nitrate instead of ammonium chloride, a little mistake here. So after the reaction has taken place, there is a lowering of the temperature. Like we said before, these will have higher potential energy, but because of the law of conservation of energy, if it gains potential energy, then its kinetic energy will get less. As a result of that, the particles will slow down, and that is manifested as a lowering of the temperature. This will remain here forever if no one interferes with that. However, if someone decides to change this from an isolated system to a closed system where energy can enter or leave, because the system is at a lower temperature than the ambient temperature, definitely energy or heat will flow from the outside into the system until it attains the original temperature here. That is why we are now saying that during an endothermic change, if the system is not an isolated one but a closed one, heat will flow from the outside into the system. As such, the system will gain energy. This is the energy profile diagram for an endothermic change as exemplified by the reaction between iodine and hydrogen. The left side of this energy profile diagram can be explained in the same way that we have done for the reaction between hydrogen and chlorine. Over this side, the molecules are approaching with their kinetic energy. They are gaining potential energy at the expense of their kinetic energy to overcome the mutual repulsion between the molecules. At this point here, the activated complex is formed that has the highest potential energy. Again, this part is associated with bone breaking, is a gain in potential energy, but a loss in kinetic energy. This part is different from the one that we did for the exothermic change. Again, the bonds are becoming stronger and stronger because of the progressive overlap of atomic orbitals. That is the energy of activation for the forward reaction. There's also what is called the energy of activation for the reverse reaction. So that is the energy of activation in the forward direction, and this is the energy of activation in the reverse direction. So look now, there's a difference here. You can see that the energy of activation in the reverse direction is less than that for the energy of activation in the forward direction. As opposed to what happened in the exothermic change, the energy of activation for the forward reaction was less than that for the reverse reaction. And there's a difference in these two activation energies that reflects the entropy change for the reaction. The difference between that reaction and this one here is that as the bonds are being formed, they do not continue gaining strength after this point here. Over this side of the diagram shows that the molecules gain all of this potential energy. But look, they did not release all the potential energy that was gained. So some of the potential energy is still locked up in these molecules here. So two things we can say. One, we can say that the product molecules will have more potential energy than the reactant molecules. As a result of that, the molecules will be at a lower temperature. The difference here between the activation energy in the forward direction and that in the reverse direction is reflective of the enthalpy change for the reaction, and that is positive in nature. You can look at that from bone energy perspective. That is the total bone energy here of the reactants, and that is the total bone energy of the products. You can see the products are having more bone energy than the reactants. So these are much less stable bonds than the reactants, and such type of reactions are called endothermic changes. I had made some questions here. You can watch that. If you want, you can answer those. Okay? Thank you for listening.